Okay, welcome to this lecture as part of a background on atomic structure and some basics that pertain to material science. This first part will look at atomic structure and a little bit of energy as it pertains to atomic and molecular structure. Okay, so as part of a review, you may recall that the atom has three components. It has electrons, protons, and neutrons. The relative masses are indicated by the information at right here. So we can see here that both a proton and a neutron are very similar in mass, and they are roughly 1.67 times 10 to the minus 27 kilograms in SI units. And we note that the electron is much lighter in mass in that it is 9.11 times 10 to the minus 31 kilograms. While your eye might be used to comparing the coefficient of these scientific notation information, to really get a sense for the scale of the mass difference between a proton and electron or a neutron and electron, inspect the exponent, that is the information given in at right in the scientific notation. So notice that we are roughly 4 orders of magnitude in difference between the neutron mass or the proton mass with that of the electron. And so actually doing a comparison, you can see here that if you were to take the mass of a proton and divide it by approximately 1840, that you would get the mass of the electron. So this is all to say that the electron is about an 1840th of the mass of a proton and a neutron. And this has consequences when we do calculations for the mass of an atom in our calculations. We often, therefore, are justified to ignore the mass of electrons as a component in molecules or atoms when we do our calculations. Okay. Next, we have the atomic number. So this is indicated on the order in which the element appears on the periodic table. And this number indicates the number of protons in the nucleus of that atom. Okay, so carbon, for example, is the 6th element in the periodic table, and so we'd expect it to have 6 protons. Now, if carbon is in a neutral condition, that means the 6 positive protons have to be canceled by an equal number of electrons. So in this case, if the atom is neutral, we can also count the number of electrons. But do be careful. Make sure that you know that the atom is neutral if you're going to count the number of electrons to determine the atomic number. Okay, as far as some mass, we have the atomic mass unit, abbreviated AMU. So one atomic mass unit is 1/12 of the mass of a carbon-12 neutral atom. So if carbon-12 has 6 protons, and we know that the total mass is 12 AMU, that must mean that there are 6 protons and 6 neutrons in the carbon-12 atom. And note that we haven't done any electron counting because the mass of the electron is so light. Okay, another way to assign mass is to count not just single atoms and use the units of AMU, but actually use count quantities of atoms that amount to realistic mass amounts that we're used to. So, for example, if we had 6.022 times 10 to the 23 atoms of carbon-12, we would have 1 gram of sample in our hands. Okay, so as you can see here, the mole, that is the 6.022 times 10 to the 23, is a nice mass. Is a nice number to use to grab collections of atoms to realize realistic masses that we're used to and can better handle in our everyday minds. Okay, so lastly, we have the idea of isotopes. So while the carbon-12 isotope will have exactly a mass of 12 grams per mole, we also know that the carbon-13 isotope with an extra neutron is also available, and that because of that extra neutron, we would expect 13 AMU or 13 grams per mole for that carbon. However, the abundance of carbon-13 is about 1.1%. So you can see that its contribution to the overall average mass of all carbon is going to be de-emphasized given how low the abundance is. So most of the carbon is carbon-12, upwards of 98.8% in abundance. And that, as a weighted average, gives us the average mass for carbon as indicated on the periodic table. Okay, and so you'll see that for lots of elements across the periodic table. Okay, so in a planetary model for the atom, something perhaps you've seen in high school, we were used to seeing the nucleus of the atom being a dense structure where all protons and all neutrons are located. And then there's a lot of empty space between that nucleus and the outermost regions of the atom, and that is where we might find the electrons. We'll see later here that we know that 2 electrons will reside in a 1s orbital condition, and that the remaining electrons will be in a 2p and a 2s orbital condition. And we'll see also later that hybridization can occur in that outermost 2s, 2p situation to lend to covalent bond formation. So, in short, the 4 exterior electrons are the 2s and 2p orbitals that are used. Okay, so as you've seen, this planetary model, of course, resembles our solar system, so it's a nice model to default to when we need to, and we'll try to do that whenever possible to keep things simple. Okay, so hopefully you've been able to sort of see the similarities here between our solar system, the nucleus being the sun, and electrons orbiting, if they are particles, in this model, just like planets around the sun. Okay, to reemphasize, we saw on the previous slide that the nucleus has the 6 protons and the 6 neutrons, and their total mass here would give us the 12. So units for this could be 6 AMU for the protons plus 6 AMU for the neutrons, and this would give a total of 12 AMU for a single carbon atom. And this is a good estimate for the mass of a single carbon atom, and we do not need to account for the mass of the electrons because they're an 18/40th of the mass of a single proton or a single AMU. Okay, and then the concept of electron neutrality, we touched on that on the previous slide. So that is, if the atom is going to be neutral, the total number of protons should equal the total number of electrons, E minus. And so if there are 6 protons in the nucleus of the carbon and this atom is neutral, we would expect 6 electrons in the empty space residing near that nucleus. And so that's what the diagram at right indicates.